طيب, okay. What we are going to talk about today, we are going to cover module 8 and 9 according to the calendar. So what we'll talk about layer 3 or network layer according to the OSI layering modules. So we'll talk about the characteristics at the beginning. So what's the network layer usually, or layer 3? Network layer, as we have discussed before, it's used to provide the services to allow end devices to exchange data. What we talked about the packets here. You know, at the transport layer, the protocol data unit is called segment, network packets, data link frame, then the bit stream at the physical layer, as we have discussed before. So the two common communication protocols used at the network layer, IPv4 and IPv6. Also, remember that when we talk about the network layer, we are talking about a logical IP address. The logical IP address, not the physical. So 32 bits in terms of the IPv4, 128 bits if we're talking about IPv6. Also, we are going to explore these IPs today as well. Now, we have also another protocols, including on the network layer, such as the routing protocol. So we have other protocols or network layer protocols included also, or include a routing protocol, such as what? ICMP. We are going to talk about it, or they call it a neighbor discovery protocol. ICMP stands for Internet Control Message Protocol. Also, there is another protocol used or implemented at the routers, such as the OSPF, Open Shortest Path First. Now, in T216A, you are going to take this course in full details, the OSPF. Now, in general, in order to complete end-to-end communication at the network layer or across the network boundary, network layer protocol perform 4 basic operations. Addressing end devices. It's very important to have a source and destination IP address, and this IP address should be configured unique on the network for each end device or host. Also, network layer performs encapsulation operation. It will receive the protocol data unit from the transport layer. It will add the IP header information, which means encapsulate the segment into a packet and generate a packet by adding what? IP headers only, okay? So what we will add when we add the IP headers information, for example, the source and destination IP address now of the sending and receiving host. Routing, select the best path to deliver the IP packets from the source to the destination. So network layer provides the services to direct the packet, in this case, to the destination host on the network. It can be located within the same network. It can be located in different network, a remote network. So in this case, we are going to forward the packets to the default gateway, and the default gateway will handle the routing and the delivery process. So packets should be processed by the router. Mute the mic, please. Mute the mic. Packet should be processed by the router. And the main rule of the router here is to select what? The best path and direct the packets toward the destination. What we call this process? A routing process. Also, network layer performs the operation of decapsulation, de-encapsulation. Packets received. Now the destination host will check the IP address, the destination IP address information. If it's matched, that host will start the process the IB by removing the IB headers from the packet. Once the packet de-encapsulated, which means we remove the IB header information now, it can be passed to the layer 4 to be processed. So decapsulation result will result what? That we have a layer 4 protocol data unit. Segments, in other way, it passed to the appropriate service at the transport layer. So when we talk about the encapsulation, as we have mentioned, what we have here, we have a layer 3 BDU, layer 4, sorry, BDU. And usually we call it a segments. So layer 3 will encapsulate layer 4 data by adding IB headers, adding additional information. So the fully segment will become a data payload. And we added a new IB header. So what we have here at layer 3, IB packets. Now, what's the information to be added? We are going to talk about it in the coming parts. So IB will encapsulate the transport layer segments. IB can use either IPv4 or IPv6 packets, and it will not impact the layer 4 segments. Now, keep in your mind, IB packet will be examined by all layer 3 devices. What I'm talking about? What are the layer 3 devices? We have talked about this many times. Routers or multi-layer switches, because they can perform the routing process at its travels or traverses from the source to the destination through the network. Now, keep in your mind something very important. IB addressing will not change from the source to the destination. Last class, when we talk about the MAC, the physical address, it should be changed and it should be a local MAC address, which means sender and receiver MAC address should be located on the same network. And we will update the physical address at each hub from the source to the destination. For the physical, it should be the same. It will not change. Source address, destination IP address, once packet is generated at the host or at the sender, it will remain the same. But in some cases, we will change the IP address. When? If we're using a NAT, network address translator. We will talk about it later. But in general, source, destination, IP address not change from the source to the destination. So NAT will change the addressing, but we are going to talk about it, the local address, later on. So we'll know why the NAT will change the IP address. Now NAT, one more time, stands for Network Address Translator. Now IB is designed or is meant to have a low. تفضل.
سؤال كذا، ايش علاقة الراوتر باللاير هذه؟ يعني ما ننتظر حتى يوصل الفيزيكال؟
اشتغل على اللاير 3. الراوتر بيقبل الاي بي باكيتس وبيسوي لها راوتنج، بيوصلها من السورس للديستنيشن نتورك. الان احنا لما نرسل بشكل عام بنسمي العمليه ايش؟ بنرسل. الان مين اللي بيرسل لك فعليا؟ انت لما ترسل اي مسج من النت عندك بالبيت، لمين بترسلها انت؟
على الجهاز الراوتر اذا موجود في البيت.
لا، ما في. اذا موجود عندك اللي شابك مع الاي اس بي موجود يعني
عندك. انا اقصد ما يوصل اللي بعدها الى اللاير 2 و1 ينتهي من هنا ويتحول خلاص.
لا 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 لا، بالراوتر. اي راوتر احنا بنعمل انكابسوليشن وديكابسوليشن. الراوتر بيحدد لمين ترسل بعدين كاي بي ادرس موجود فيها عن طريق الراوتنج اوبريشن، راوتنج تيبل. انت بترسل بت ستريمز دائما الارسال النهائي بيكون وين؟ على الفيزيكال لاير. ولكن كل لاير له تاسك. الآن واحدة من عمليات توصيل المسج، خلينا نقول ان جنرال محتاجين نسوي راوتينج، كيف من أي طريق أمشي، هذه بتصير على لاير 3. الباكيتس بصير توصيلها على لاير 3. الآن أنت بترسل للسويتش باللان، السويتش لازم يشيك الاي بي ادرس، اذا لوكالي بيساوي على طول ايش؟ سويتشنج على الديستنيشن بورد، فهذا ديليفرنج للباكيت. وصلت؟
نعم نعم، الله يرضى عليك، شكرا لك دكتور.
الله يسعدك. بنشتغل على كل اللايرز بالسند والريسيف، كل اللاير، لانه كل لاير له تاسك. اتفقنا احنا كل لاير له وظيفه، ما بنقدر نقول لاير واحد بيساوي كل شيء. وقتها ما راح
يعني ما انتهى الاجراء هنا، حيستمر
لا
وحيشتغل
لا لا
لاير
لا
2
لا
ولاير 1.
لسه عندي السيجمنت، وبعد السيجمنت بدي ارجعها لليوزر داتا لحد ما توصل الابلكيشن لاير. احنا ليش قاعدين بنشرح كل لاير لوحده؟
وضحت، شكرا لك.
يعطيك العافيه. يلا الان بالله ركزوا معنا هنا. الان ان جنرال الاي بي، انا بتكلم عن نتورك لاير هنا، تمام؟ الاي بي باكيتس اور الاي بي هنا designed to have a low overhead. ليش الاوفر هيد قليل جدا باللاير هذا؟ simply because it's provide only the function needed to deliver the packets from the source to the destination over interconnected network. Which means what? IP protocol was not designed to track which packets received, which packets is lost, sequencing, flowing the data packets. It's not implemented at all. Okay? If we need this function, it can be performed by other protocol at different layer. ركز معي الطالب اللي سألني. شوف, if I want to manage the flow of the packets, if I want to trace the flow of the packets, I can, but I will use a different protocol at layer 4. At layer 4 now. Which protocol? TCP. So why the IB provide a low overhead? Because it's provide only the function to deliver packets from the source to the destination. There is no any management or flow control tasks or operation operated at this layer. Keep it in your mind. So according to that, we can say IB is a connectionless. IB is best effort. IB is media independent. So what does connectionless means? Best effort means, media independent means. Now we have a connectionless and connection oriented actually. Connectionless means IB does not establish a connection with a destination before sending the packets. So it's like the routing. This is the routing. We will not create a connection between the sender and the receiver, then the packets will be transmitted through this connection type. Give us an example about a connection established before any sending operation is performed. A phone call. You must establish the connection, then the transmission can be started. So, in case of the network layer, it's a connectionless. There is no control for the information needed. We do not need any controlling for synchronization, acknowledgement. I have received the packet, send me the next one. There is no acknowledgement. The destination will receive the packets when it's arrived, but no pre-notifications are sent by IB. Also, if there is a need here for connection-oriented traffic, if there is an organization, flow control, acknowledgement, managing, establish the connection, then start the transmission. You can use another protocol at different layer. Which protocol, as I have mentioned? Transmission Control Protocol, TCP. So, guarantee of the delivery performed at layer 4. لأن نتأكد المسج وصلت أو لا. هذا layer 4 مش layer 3. الديستنيشن موجود أو لا. هذه مش مشكلتي الآن باللاير هذا. هذه مشكلة اللاير اللي فوق. later on. So remember, each layer have a different function, different protocols, different tasks. IP packets provide best effort. We already talked that we have what? A low overhead. So low overhead. So IP does not require any additional fields in the header to maintain an established connection. It's a connectionless. So since it's a connectionless, we have reduced the overhead of the IP. So with no pre-established end-to-end connection, sender will not be aware that the destination device is presented or not, the sending packets arrived or not, or if some of the packets were lost, or the destination device able to access and read the packets. So in general, it's IP is a best effort. We're talking about the management here and the tracing. So IP will not guarantee the delivery of the packets. IP has reduced the overhead since there is no mechanism to resend data that is not received. As you see here in the example, we have sent IP packet 1, 2, 3. Only we receive 1 and 2. The sender will not resend IP packet 3. It does not expect an acknowledgement. Thank you, I have received the packets correctly. We are going to perform these tasks at different layers. It's the TCP protocol responsibility in other way, not the IP protocol responsibility. IP does not know if the other device is operational or not, or if it's received the packets or not. So we can say IP is unreliable. It cannot manage or fixed and delivered or corrupted packets. It cannot retransmit after an error occurred. It cannot realign out the sequence of packets, sequencing, with segmentation. It must rely on the other protocol for these functions. My question, which function can perform all of the above mentioned tasks؟ قلت اسمه أكثر من مرة. إيش البروتوكول؟
TCP.
Thank you. TCP. ما تجاوبيني كأنك بتسألي، جاوبيني إنه جواب. نعم TCP. So finally, IP is media independent. Let me simplify it to you. What does media independent? We are going to send an IP packet. What we have here? A copper connection. What we have? A wireless. What we have? Optical. What we have? Wireless. So IP does not concern itself with the type of the frame. So I'm talking about layer 2 now, required at the data link layer, or the media type for the bit stream at the physical layer. It can be sent over any media type, copper cables, fiber, or wireless. So in general, IP is media independent. Now, please focus here. What I'm going to talk about performed at the router, or it's a task of the router in some cases. So, the network layer will establish the maximum transmission MTU. Network layer receives this from control information sent by the data link layer from layer 2. The network then establishes the MTU size. Do you remember the segmentation? Segmenting. We have a larger packet or we have a larger data. We are going to cut it or split it into small pieces called segments, and then sequencing the segments. It's very similar to this, but it can perform sometimes at the router what we call it. بالله ركزوا. It can be performed at layer 3 devices. Layer 3, I'm talking about the router or the multi-layer switches. So what the router or layer 3 devices will do will split, will cut the IP packets into smaller maximum transmission unit. What we call this fragmentation. So where is the fragmentation operated? At layer 3 by layer 3 devices such as router multi-layer switch. So fragmenting causes latency. IPv6 does not fragment the packets. Keep it in your mind. I'm talking about only IPv4 here. Example, if the router goes from Ethernet to slow one with a smaller MTU. So my data is larger than the network bandwidth and its ability to receive. So I need to send a lower amount of data, reduce the amount of data transmitted in this case. So what we are going to do, split, reduce the size, send multiple MTUs. Which device will perform the fragmentation operation over the fragmenting process here? Layer 3 devices, which are the router. But it's not always operated, sometimes, not always. واضح؟ طيب, now, what we have said when we talk about the encapsulation, IP will receive the BDU protocol data unit segment encapsulated by adding additional header information. What we call this a process, IP, what's the output? Packets or IP packets. So IPv4 is the primary communication protocol for the network layer. The network header has many purposes, many functions, many tasks. Why we need the network header or the IP header? To ensure the packets is sent to the correct destination or to the destination. Why? We will add the destination IP address, or we have it. It contains information for the network layer processing in various fields, different fields, as you will see in next slide. The information in the header is used by all layer 3 devices that handle the packets. So let us have a check about IPv4 network headers. What you are seeing here is the IPv4 network header. Keep in your mind each line here or each row size is 4 bytes. So how many rows we have? 1, 2, 3, 4, 5. 4 by 5, so the total is 20 bytes. So IPv4 network headers characteristics are the following. It's in binary. It contains several fields of information. We are going to talk about each field quickly. How we read the diagram, we read it from the left to right, 4 bytes per line, top down. Now, the two most important fields are the source and the destination IP address. 32 bits source IP address, 32 bits destination IP address. Protocols may have one or more functions. Now, let us talk about the most important fields here. We'll start with a version. 4 bytes, it contains 4-bit, not bytes, binary value, and its value always set to 0, 0, 1, 0 in case it's IPv4 packets. If it's IPv6, we'll have the version, but it will be 0, 1, 1, 0. So 0, 0, 1, 0, it's a 4 actually. 0, 1, 1, 0, 6. From binary to decimal, converted. Now, I'm going to talk about this, the DS. DS is called differentiated services or DiffServ DS. It used, or usually it's called, the type of the services. We identify the type of the services here. DS is 8 bits, as you see, 1 byte, and it's divided into 2 parts. The 6 most significant bits from the left, it's called differentiated services code point bits, and the last 2 bits here, the ECN, are explicit congestion notification. So usually we use it to identify the service, to determine the priority of each packet. As you know, we have a prioritization, priority. Voice packets will treat it or will have a higher priority than the web packets. So how we will identify the priority? By using this field. Now I'm going to jump to the header checksum. One by one. Header checksum is used to detect a corruption, in case we have any corrupted data in the IPv4 headers. Now, next one, let us talk about this one, time to live. And we can stand it or shortcut the name to TTL, time to live. What's the time to live? It's 8 bits binary value used in order to control the lifetime of the packets, how long the packets can remain on the network. And its initial value, 64 seconds, and the largest or the maximum value, as it's 8 bits, 8 ones, 255 seconds. Now, why we need it? Now, the source device will set the initial TTL value, and the TTL will be decreased by 1. It will be subtracted by 1 at each time the packet is processed by the router, which means from hub to another one, the router will reduce the TTL by 1, minus 1. Now, if the TTL file decremented to 0 before it's received its destination, what the router will do in this case? The router will discard the packets, will ignore, delete the packets, and the router will send something called ICMP, time exceeds message, Internet Control Message Protocol time exceeds message, to the source, to the sender. Why? In order to inform the sender that your message was not delivered to the destination IP address because the time to live field was exceeds, which means what? It reached 0. So for example, we set it to 255 seconds and it was decremented 255 times by 1, so it became a 0. Now what the router will do? Discard it, send ICMP time exceeds message to the source, to the sender, informing the source packets will not received because of the TTL field reaches 0. Keep in your mind one important point as well when I'm talking about this field in the context of the IPv4, not 6. At each hop or at each time the TTL is reduced by 1, the router must recalculate the header checksum. Now, this condition is not available or it will not be implemented for the IPv6, only for 4. At each hub, which means TTL reduced or decremented by 1, we need to recalculate the header checksum. Who will recalculate it? The routers. Now, next field, the protocol, and usually 8 bits binary, and usually will contain the following or one of the following 3 protocols, either ICMP, or TCP or UDP. So it's used to indicate the data type of the packets, which will enable the network layer to pass the data to the appropriate upper layer. So what's the data type to pass it to the upper layer? It's a ICMP, TCP, or UDP. Source IP address, 32 bits of the sender, IPv4 address, and it's always unicast, one address. Destination IP address, 32 bits binary of the destination. It can be a unicast, one-to-one. It can be a multicast, one-to-many but not all, or it can be a broadcast, one-to-all. Now, what about internet header length? What about total length? What about header checksum? These fields usually used to identify and to validate the packets. We have another fields as well used to reorder the fragmented packets. Another fields will be used to reorder the fragmented packets, the MTU. Here, what are these fields? Are the following: identification, flags, and fragment offset. It's used to keep track the fragments or of the fragments. So why? Because the router sometimes have to split the IP packets when it's forwarding from one medium to another medium, such as what we have mentioned here, from Ethernet to slow WAN network, where wide area network, slower one. So we need to fragment the packet in this case. This table summarizes all what we have discussed about the fields. You may refer to the Net Academy and you will find all the details I have discussed when I was talking about the IPv4 header here. So now, let us talk about the limitation of the IPv4. IPv4 in general have three major limitations. First one, IPv4 address depletion, which means we are running out. There is no unique IPv4 addresses available now. So IPv4 has a limit number of unique public now, public, not a private, addresses available. So in general, we have up or approximately, we have 4 billion unique public IPv4 address. Is it enough? No. Many devices, many services, many regions keep developed, so the need or the request of a global unique IPv4 addresses is increased. So simply we are running out. ما عنا الآن ما في unique IPv4 address تعطي له سايت جديد. ما بتكلم local IP address، ما بتكلم LAN، بتكلم على انترنت WAN. الآن ما عندي، خلصنا ال 4 billion IPv4 addresses. الآن another important is the lack of end-to-end connectivity. To make the IPv4 survive this long, private addressing and NAT were created. I will explain this now. This ended the direct communication with public addressing. Now, in order to handle the previous or the first problem, one of the solutions suggested to handle the limitation or the limit number of the IPv4 is to use something NAT, Network Address Translator. So Network Address Translator usually implemented within the IPv4 NAT6. What is used? It's used to provide multiple devices. So multiple devices can share one public IPv4 address. So let me say 10 private IPv4 addresses will share only one public IPv4 address. So NAT provide a way for multiple devices, in this case, to share a single address. Now, because the public address is shared, the IPv4 address of the internal network host is hidden. So I don't know what's the actual host of the IP of the device. We are using the public. The private translated to a public address, so are we using the public address. So the hidden of the private address or the actual address of the device will cause a problem. What's the problem? Sometimes we need end-to-end connectivity, one-to-one connectivity. So we are using a public NAT address, not the actual address. Many devices sharing one public address or using one public address. So end-to-end connectivity is not available in such cases. Also, keep in your mind, when we talk about NAT, Network Address Translator, we are adding more latency, more complexity, more problems. So it will cause the latency, it will cause many problems for troubleshooting issues, maintaining issues. Why? Multiple address will share a single global one. So it's like that what NAT is used to share one public address to multiple devices, not or to multiple hosts, not a single one. Now, in order to handle all the previously mentioned the problem here, what we have IPv6. So IPv6 was developed by Internet Engineering Task Force, IETF. IPv6 overcomes all the limitations of the IPv4. Also, لحظة بالله. Sorry, always improves or improvements that IPv6 provides the following. Now, IPv4 is 32 bits. Maximum number of public unique IPv4 address, as we have mentioned before, approximately 4 billion address. Now, IPv6 is 128 bits. 128 bits. So we have 10 to the power 36, 10 to the power 36 unique IPv6 address among the world, which called one undecillion, the number, when we have 36 0. So باختصار let me simplify it to you. إذا بدنا نجيب الرمل بالبحر ونعطي كل حبة رمل IPv6 unique address راح يضل عنا available IPv6 addresses. باختصار. This is an example. Also improved the packet handling. As you will see, some fields removed no longer will be used in the IPv6 headers. Also eliminates the need of NAT. Since there is a huge amount of addressing, no need to use any private addressing, no need to share a single public to multiple or between multiple private addressing. So NAT is not needed at all. Network address translator is not needed for the IPv6. واضحة هذه؟ So what we have here, we have the IPv6 headers. As you see, 4 bytes per line. It reads from the left to right, top down. Usually, the IPv6 header is fixed at 40 bytes or long, while IPv4 is what? 20 bytes. So as you see, some of the field remains the same, like the version, source address, destination address. Some of them change the name and change the position, such as the traffic class instead of differentiated services, payload length for the data next header, and hop limit for the TTL. Some of fields no longer is used. It will not use flag, fragment offset, header checksum. It's totally removed to improve the performance compared with IPv4. So let's talk about the headers version. It's a 4 bits binary, but what's its value now? 0, 1, 1, 0 from the right to the left. While what's the value was for the IPv4? 0, 0, 1, 0. So this one is used to identify that this is IPv6 packets, not IPv4. 0, 1, 1, 0. Traffic class 8 bits equivalent to the DS, the differentiated services, in order to identify the priority of the packets. Now flow label 20 bits field, and it's used, or field suggests that all the packets with the same flow label will receive the same type of handling. Same packets with same label, same type, will be treated by the same treatments at the router. Payload length, it's 16 bits fields, indicates the length of the data portion or the payload of the IPv6 packets. It will not include here the length of the IPv6 header, which fixed to 40 bytes. So the pay length is not included within this 40 bytes payload length. It's the layer 4 actually data segment. Now next header, 8 bits equivalent to the IPv4 protocol fields. So it's equivalent to the what? To the protocol fields, which protocol to be used on the upper layer. So it can be ICMP V, or it can be ICMP TCP, as we have mentioned before, or UDP. Next header, ICMP, TCP, or UDP. Next level protocol or layer 4 protocol. Now, hop limit, it's equivalent to the TTL. As you see, this value will be decremented, reduced by 1 at each router that forward the packets. So at each hop, the next or the hop limit will be reduced by 1. When the counter reaches 0, the packets will be discarded as well, and the router will send internet control message protocol version 6 here, ICMP v6 time exceed message will be forwarded to the sending host, informing the sending host that this packet was not delivered to the destination because the hop limit reaches 0 or exceeds. But keep in your mind, for IPv4, the router should recalculate the checksum. But since we have a lower overhead here, better performance, no checksum is needed. No checksum will be recalculated by each router when we decrement the hop limit fields by 1. So we are going to improve the network performance in this case. We will not recalculate the checksum. We do not have a checksum fields actually. Source IP address 128 bits written on the hexadecimal, as you will see later on. Sender address or sending host address destination 128 bits field identify the receiving host or the destination address. Finally, when we talk about the packets, IPv6 may also contain some extension headers, optional, not mandatory, optional headers. So, extension headers characteristics are the following. Provide optional network layer information, optional information, are optional in general, placed between IPv6 header and the payload. It may be used for fragmentation, security, mobility supports. Keep in your mind, unlike the IPv4, routers do not fragment the IPv6 packets. There is no fragmentation here for the IPv6 packets. Any questions? طبعا keep in your mind please, it's very important to refer to the NetAcad. It's very important to watch these videos. It will simplify everything to you, packets header, task of each field, what it's used for, and so on. It's very useful to study from the NetAcad, not only from the PowerPoint presentation. In your mind this. Now, how the host routes. With both IPv4 and IPv6, packets are always created at the source host. So the source host must be able, in this case, to direct the packets to the destination host. Now, in order to do this, host end devices will have their own routing table. So what we are going to talk about, the routing table of the host devices. أي جدول معلش؟ هذا أحلام تتكلمي عن الرو هذا؟ لا شوفي شو كاتب لك. This will be for version 6 as opposite to version 4. Version 4, the field will be like this one. If we are talking about IPv4 headers, the version value will be 0010. Now, we are talking about the version field of IPv6, so the value is 011. What's this decimal number يا جماعة؟ حولوا لي هذه لديسيمال.
دكتور أنا أقصد السورس اي بي فيرجن 4 اللي هو آخر صفين.
هذا؟
في الجدول اللي قبل شوي آخر صفين مكتوب السورس اي بي فيرجن 4 والمفترض 6.
اوكي. ثانك يو. على فكرة في أخطاء. نعم وارد يعني مس تايب، وحتى الرسمة المحاضرة الماضية عدلنا على النتورك فيها. ثانك يو. والله ما انتبهت لها. ثانك يو. طيب الآن شوفوا، كل هوست راح يكون عنده راوتينج تيبل. Keep it in your mind. So each host device create their own routing table. I need to add the destination IPv6 address or IPv4 regardless now. طيب الhost, any host can send the packets to the following. Any host can send the packets to the following host. The host can send a packet to itself. The host can ping itself. So if it's IPv4, we'll use the IP 172.0.0.1 وهذا معروف، هذا local host أو بيسموه loop back interface. Open the CMD ping 172.0.0.1, you will see that the ping is working correctly. So what you are going to do here, you are pinging yourself. We call it a loopback interface. Also, we have a loopback interface for IPv6 ended with ::1. We'll talk about this later, the double colon, what it means. So, ::1, it's a local interface or loopback interface for IPv6. Also, as a sending host, I can send a packets to any other devices located on the same LAN. So PC1 can send the packets to another PC located on the same LAN, as you see here. So what's the IP of this PC? 192.168.10.10. What this one? 192.168.10.15. Now the prefix is 24. What's this 24? In full details, the subnetting, we are going to talk about it inshallah next week. Now what we have here, we have the default gateway. What's the IP of the default gateway? R1 192.168.10. This is the network address, the network portion. .1, this is the host portion. So we can send the packets to ourselves as a host to any local hosts or remote hosts, like the server located in different network, not on the same network. Now, the source device determines whether the destination is local or remote. The source device will decide if the destination is locally or not. How? Simply, we are going to use the methods of determination. If we're using IPv4, source host uses its own IP address and the subnet mask. What's the subnet mask? We'll talk about it next class, inshallah, along with the destination IP address. So keep in your mind, we need this 3 inputs, let me say, to determine if the host is located locally or on different network. In case we are talking about IPv6, the source or the sender uses the network address and the prefix advertised by local address. So we need 2 inputs in this case. Also, we are going to discuss them in full details in advanced topics. Now, usually, local traffic is sent out of the host interface to be handled by the intermediary devices. For example, PC1 will send the packets to the switch. This is an intermediary local device. The switch will examine the destination IP address, will check its own table or MAC table, or by using that, then it can be switched to the receiver one. Or it can be sent directly from PC1 in this case to the switch, from the switch to the gateway will send it outside in case we are going to send the packets to a device located on remote network, not LAN network. So either locally or globally, let me say, through the gateway. So remote traffic is forwarded directly to the gateway on the LAN. So the destination IP address here will be what? The destination MAC will be what? R1 interface 1 MAC address, as we have discussed last week. So what's the default gateway? Your interface to the internet network, simply. Your LAN interface to the global network. So a router or layer 3 switch can be a default gateway. Features of the default gateway are it must have IP address in the same range as the rest of LANs. As you see here, we have a local IP address for the default gateway, R1, 192.168.10.1. It must have IP address locally. It can accept the data from the LAN and is capable of forwarding the traffic of the LAN. So it will receive the local data from LAN through, let me say, interface 1. It will forward it to the global through interface 2 here. We have another Ethernet here for the router. Local gateway and a global gateway, let me say. It can route to other networks. Now, what if the device has no default gateway or a bad default gateway? Simply the traffic will not be able to leave the LAN. End devices on the LAN without a gateway cannot send any packets outside this LAN. Simply like this. So, when we talk about the host, how the host will learn, will know about the default gateway. The host will know the default gateway either statically, when we configure the IP address or the interface, we can statically configure the default gateway address, or it can be dynamically through DHCP protocol, dynamic host configuration protocol. IPv6 also sends the default gateway through the router solicitation or can be configured manually. So what's the router solicitation, router advertisement, neighbor discovery, neighbor advertisement or replay? We are going to talk about it, I think, this meeting today on Unit 9. The default gateway is a static route, will be at least, or will be, sorry, the last resort route in the routing table. Now, any packets sent outside the local network, its last, let me say, terminal, last stop, last resort will be the gateway of the router. All devices on the LAN will need a default gateway of a router if they intended to send the traffic remotely or globally. Otherwise, they cannot send any data outside this LAN in case the default gateway was not configured at each device. So, how we can see the routing table at each host? Remember, each host will what? Will have its own routing table. We have a routing table. So on Windows, route print or net state -R can be used to display the routing table. So as you see here, we are using the CMD, the command prompt. Just type this command, net state -R, as an argument. It will list to you the local routing table at this PC or this hosts. Usually, when we run this command, we will have 3 different sections will be displayed by these 2 commands. What are the commands? Route print, or we can use this command. First section will list all the potential interfaces and the MAC addresses or addressing. Second part, IPv4 table, the interface. and subnet mask, network destination. Gateway, as you see here, the gateway is 192.168.10.0. How we can reach it at interface 192.168.10.0. For example, we can reach 192.168.10.1 through 192.168.10.10 and so on. We'll talk about it in full details. Hold on. Or it can be IPv6 routing table. So 3 sections: interfaces, version 4, and version 6. How we can list or check these data? Run cmd, type route print or netstate -r. Now let us understand what's the routing. What's the routing? We talk about the routing. This is a routing table example. For example, for router 1. Router 1 can reach the network 192.168.10.0 through gigabit Ethernet 000. Router 1 can reach the network 165.200.244. This is the network address through gigabit Ethernet 001. Router 1 can reach remote network 10.1.2.0/24, the prefix 24, through what? Through router 2, via router 2, globally here. So router 2 is the gateway actually for router 1. So the default route, it's the default gateway is router 2 in this case for router 1. So what happens when the router receives a frame from the host devices? What the router will do when the router receives this from the local network? PC1 wants to communicate PC2 at a remote network. So simply the packets will arrive on gigabit Ethernet 000, which is the default gateway here, interface of router 1. Now router 1 will de-encapsulate layer 2 Ethernet header and the trailer, as we have discussed. Router 2 will what? Re-encapsulate. Now router 1 examines the destination IPv4 address of the packets and search for the best match. Now once we encapsulate it, the router 1 will check what's the destination IPv4 address. Now we have 10.1.1.10. Router 1 will check its routing table. So how I can reach the network 10.1.1.0 through router 2. So this is the network. What about this 10? It's the host portion. So once the router reads the destination address, the router will do a matching or a best match with its own IPv4 routing table. The router then, the route entry indicates that this packet should be or to be forwarded to router 2. Now router 1 encapsulates the packets into a new Ethernet header and trailer and forward the packets to the next hub router. So when the router de-encapsulates the packets here, it will examine the destination IPv address. It will do a matching with a table. Now we'll re-encapsulate or add a new header and the trailer, but remember, router 1 will change the destination. The source MAC address will be router 1 interface G001, and the destination MAC address will be the MAC address of what? Of router 2 at this local interface. Always MAC address. Data link layer is local address. So because of this, we re-encapsulate, check the IP, encapsulate, de-encapsulate, sorry, check the IP, re-encapsulate, then forward. So, how we can understand any router table? Please focus with this one. The routing table of the router contains network route entries listing all the possible known network destinations. All the networks can be reached by this router. This is what we have, or through which interface on the routing table, as you see here. Now, in general, we have three types of routes in the routing table. Three types of entries, let me say, or routes on routing table. Three options. It can be directly connected, or remote, or default route. So what I mean by directly connected? These routes are automatically added by the router, provided the interface is active and has an address. So router 1 directly connected through Gigabit Ethernet 000 to WATS network 192.168.10.0 prefix 24. Router 1 is directly connected through Gigabit Ethernet 001 to network 209.165.200.224. So this is what does directly connected means. We have two directly connected networks here. Now, remote network. These are the routes the router does not have directly connected and may be learned. The router will learn about a remote network. So where is the remote network here? 10.2.0. So router 1 will learn about this network. This network can be reached through or via router 2. So how the router will learn? Either manually, so we'll configure or add it to the routing table, let me say, or dynamically. Dynamically by using what? Some dynamic routing protocols, such as OSPF, Open Shortest Path for Pairs, or we can use EIGRP, which stands for Enhanced Interior Gateway Routing Protocol. Now, finally, default route, default gateway. If the router did not find any match in its routing table, it will be forwarded to the default route next hub. So this forward all the traffic to specific direction when there is no match in the routing table. So R2 is the default route. R2 also will be used to reach remote network, and router 1 will learn about it either manually or dynamically. So what's the difference between static routing and dynamic routing? Check this one. Static route characteristics must be configured manually, must be adjusted manually by the administrator when there is a change in the topology. Good for small, non-redundant networks, usually used in conjunction with a dynamic routing protocol for configuring the default route. Now check this one, how we can configure R1 statically. So what we will use at the global configuration level, R1 config 1, we will use IP route comments. So IP route will be followed by the remote network address 10.1.1.0 with its subnet mask 255.255.255.0. Now it will be very simple to you to know what's this number and this number next class. Now we need to mention router 1 can reach this network through what? Through what? 209.165.200 dot, not the network address here. We add what? The interface address 226. So this is the next hub. So IP route, remote network address, followed by the next hub router address 209.165.200, not 224. This is the network address 226. Now, in case the network updated, we must change the static routing manually. It should be reconfigured at each update of the network topology. So this is the main drawbacks. أي تغييرات بتصير على النتورك لازم ترجع تساوي configuration للstatic routing details. Now for the dynamic, it's dynamically like the open shortest path. First, router will automatically discover the remote network, maintain up-to-date information, select the best path of the destination, find the new best path when there is a topology changes. So dynamic routing can also share a static default route with other routers. So for example here, router 1 will using which dynamic protocol? Open shortest path first to learn about R2 network. And R2 will use the same network to learn about R1. Now in case the connection between R1 and R2 is not available, R1 will learn about the next new path automatically. So R1 will connect now to the remote network through R3. R3 now will connect it to 2. 2 will deliver the packets to the local network. So routing table can be learned dynamically or statically. Remember, we have a direct connected remote default route entries on the routing table. Now the question, how I can show my router routing table? Before we talk about it, check this one. Router 1 have a direct connected with this LAN 192.168.10.0. Router 1 directly connected with 209.165.200.224. This is the network address. Router 1 have a local link to this LAN through this interface G000. What's the IP for this interface? 192.168.10.1. Router 1 connected to this network through 209.165.200.225. We have a remote network here 10.1.1. It should be .1, not .2. As you see here, .1.1.1.0. So, how we can see the router or the routing table, display the routing table for any router? Simply at what's this level? What's this configuration level? Router 1 hash. Privileged. Now, tamam. What's the router? Show IP route. Show IP route. Now, I'm going to explain to you how to understand this. And you just match it here. Do a matching here. Now, show IP route command shows the following route source. It will give you the following sources. The following. If we have L, means directly connected local interface IP address. Directly connected local interface IP address. So for router 1, 192.168.10.1 is L, directly connected IP interface. Where is it? This one. Directly connected using gigabit Ethernet 00. Now C, directly connected network. So local, it's the local IP address to the interface. C is directly connected network. It's the network address. So as you see here, directly connected to the network. Which network? 192.168.10.0, the prefix the 24 is directly connected network now through gigabit Ethernet 000. So this is the local link IP address, and it's a directly connected to this network. So interface gigabit Ethernet 000 is directly or local directly connected to 209.165.200.255. It's directly connected to the network 209.165.200.224. Check the last two lines or four lines here, the C and the L. So S means static route, which was manually configured by the administrator by using IP route followed by the argument. So as we see here, we have S. So router 1 connected to network 10.0.0.1, or sorry, router 1 here configured to connect to the default gateway, to the default network 209.165.200.226. So the default route for R1 is what? Interface 209.165.200.226. O means Open Shortest Path Protocol, Dynamic Learning Protocol. And also it can be D, means also we are using the Enhanced Interior Gateway Routing Protocol, not the OSPF. So this command will show three types of route. Now this is the routes. These commands, L, what it means, C, what it means, S, O, and D. It can show directly connected, C, L. Now the L is the local IP address, the C is the local network address, O or D, which means the router learned about the network by using the routing protocols. S with asterisk, always the default route. So if we check this, we have a default route, we have link, local link, directly connected network, and we have a layered network by using the Open Shortest Path Protocol. Router 1 can reach the network 10.1.1.0 via what? Via or through router 2 gateway 209.165.200.226 by Ethernet gigabit Ethernet 001. So in this table, we have two directly connected networks. In our example, which are the two directly connected networks? It might be the question like this in the quiz. Given this figure, what are the two directly connected networks of router 1 or of router 2, let us say, of router 2? Of router 2, you will say the first directly connected network 209.165.200.224. The other network 10.1.1. It's .1, not .2, .0. Remote network, the code will be O or D, and we have here one remote network. So in this example, router 1 has a route entry for network 10.1.1.0 that is learned dynamically here from router 2 by using open shortest path first protocol. Also, we have a default route which is actually interface 1 of router 2, the IP which ended by 226. في أي سؤال هنا قبل ما نبدأ بموديول 9؟ طيب, just wait. Don't worry, 9 is shorter than 8. It's very short actually, it will not take a long time. Just let me share it and we'll listen. What we are going to talk about, two important protocols. Address resolution. Address resolution. Now, we need to know what's the MAC address for a given IP address simply. So, what we are going to talk about, the MAC address and the IP address as a revision. Now, there are two primary addresses actually assigned to a device on the Ethernet LAN. We have the physical layer 2 address, data link layer address, or we can call it the MAC address, used for network interface card to another network interface card communication on the same Ethernet. Remember, always the MAC should be local address, not like the source IPv4 and destination IPv4. We have layer 3 logical address or the IP address used to send the packet from the source device to the destination device. Now, layer 2 addresses are used to deliver the frame from one NIC to another NIC on the same network. On the same network. This is for the last time. Now, if the destination IP address on the same network, the destination MAC address will be that of the destination device. So PC1 would like to send the packets or a message to PC2. So the source MAC address of PC1 is not added, AA. Now the destination MAC address of PC2 is added as well. It's located locally on the same network. So 555555. Now, as you see, the source IP address as a logical IP address added 192.168.10.10, and the destination also 192.168.10.11. Now, what's the network address for this network? 192.168.10.0. What's the subnet mask? 255.255.255.0. However, PC1 will know from the IP address that this device located in the same network because they have the same network portion for the source and destination. So, now, what will happen when we want to send to a destination device located on a remote network, not a local network? So here the destination is located on the same network. What if the destination device located on a remote network? Now, routers in this case will be included in this process. So the routers will check the destination IP address in order to determine the best path to forward this IPv4 packets. So once the router receives the Ethernet frame, the router will de-encapsulate layer 2 frame. The router will use the destination IPv4 address, the logical address, to determine the next hub, to which device will be sent next. After that, the router will encapsulate the IPv4 packets in a new data link frame for the outgoing interface. So the router will receive now PC1 need to send to PC2. So PC1 will send it to router 1. So the source, as you see here, MAC address is the source of the sender. Now the destination is the gateway destination, is the MAC address of the default gateway. But the source IPv4 address will be PC10 IP address. Destination IP address will be what? PC2 IP address 10.1.1.10. So PC1 will send it to the router. The router will de-encapsulate, will check what? The destination IPv4 address. This one. The router will do a matching with a routing table to select the best path. Once it's done, the router will re-encapsulate the packet, create a new data link frame to be sent to the next hub. Where is the next hub? Router 2. So when router 1 send it to router 2, what's the source MAC address here? And what's the destination MAC address? The source MAC address will be the MAC address of Gigabit Ethernet 001. And the destination MAC address will be the interface of router 2. Gigabit Ethernet 001, which DDDDDD. What about the source IP address? Same. What about the destination IP address? Same. Now router 2 will repeat the process. De-encapsulate, check the IP address, destination, re-encapsulate. What router 2 will update? Source MAC address, destination MAC address. Why? Because the source and destination MAC should be a local address. Now, so when the destination IP address in the remote network, destination MAC address is that of the default gateway, as we have mentioned here. Now, what's the ARP protocol and what's the ICMP? ARP stands for Address Resolution Protocol. ARP is used by IPv4 to associate, to map the IPv4 address of a device with a MAC address. What does that mean? Simply, sometimes PC1 will not know what's the MAC address of the router. I have only the logical address. So how I will get the MAC address of Gigabit Ethernet 000 in this case? By using a protocol named ARP protocol, Address Resolution Protocol. So it's used to map address to MAC address, logical IP address to physical address. What if we are using IPv6? We will use Internet Control Message Protocol version 6. It's used by IPv6 to associate, to map the IPv6 address of a device with the MAC address of device. So let us see how ARP is working, how ICMPv6 is working. Remember, main goal is what? The main goal is what? To get the MAC address. I don't know what's the MAC address. I have only the IP address. Simply like this. So the devices will use on the IPv4 address resolution protocol to determine the destination MAC address of a local device when it knows its IPv4 address. So let me simplify it to you. Check this one. PC1 or H1 want to send a message to H3. Now H1 have only the IP address. Only we have 192.168.1.8. So we need what? We need the destination. So how H1 will know? By using the ARP protocol. So H1 will say like this: I need to send information to 7 here, they said it, for example. 192.168.1.7. I need to send to H4, but I don't know the MAC address. So how I can get the MAC address? By using address resolution protocol. So ARP simply provide two main functions. The first function, resolving the IPv4 address to MAC address, or mapping, let us say, maintaining ARP table of IPv4 to MAC address mapping. So we'll have an ARP table. So address resolution protocol, what we need to convert the IPv4 address to MAC address. So in order to send a packet to another host on the same network, the host must know the IPv4 address and the MAC address of the destination device. So how we can know the MAC address? By resolve it by using the ARP protocol. So how the ARP is working, how the ARP is functioning. To send a frame, the device will search its ARP table. Now any device will check the locally ARP table for the destination IP address and corresponding MAC. So I want to send as BC1 a message to BC10. I will check my ARP table as BC1. I have this IP address. Where is the MAC address? Now, if the packet's destination IP address on the same network, the device will search ARP table for the destination address. Now, sender and receiver located on the same network. So I will check what? My ARP table to link this IP or to map this IP to a MAC address. Now, if the destination IP address is on different network, the device will search the ARP table for the default gateway. So, in both cases, if the destination on the same network or on different network, we are going what? To search the ARP table. And sometimes we call it the ARP cache table. And keep in your mind, this table is stored at each device temporarily on the RAM, on the random access memory. It's not a permanent table. So, if the devices after the searching on step 1 and step 2, after we're done with this one, so in both cases we should search for IPv4 and corresponding MAC address, either if they are locally or we will send it to the default gateway. So we need the IP address and the gateway MAC address. So if the device locates the IPv4 address, its corresponding address or MAC address is used at destination MAC in the frame. If we find the IPv4 address and the MAC on our table, we can add the source, we can add the destination, we can done with this. What if we do not find a match? If there is no ARP table entry is found, then the device will send ARP request, address resolution protocol request, to know kindly send to me the MAC address of this IP address. It's like this. This is the ARP request. So how the ARP request is done, or when, before we say how, please, you must watch this video. It's very simple and easy. I will explain it, but you should watch it. Now, suppose the device check the destination IP address. It's located on the same network, let us say. So now the device, the sending device, examining its ARP table. There is no match. So the device must learn. I need to know what's the MAC address associated with this IP address. So the sending device will send ARP request. Usually the ARP message will directly encapsulate it within the Ethernet frame, which means there is no IPv4 header. There is no IPv4 header. So the ARP message will be encapsulated in Ethernet frame by using 3 headers only. Destination MAC address, source MAC address, and the type. Now, what's the destination MAC address? Because it's locally, it will be a broadcast address. What's the broadcast address? FF, as we learned last class. So the ARP request will be transmitted to the all NICs, network interface cards, on the LAN, except of the sending device. Now, all the Ethernet on the LAN have to accept and process the ARP request. They should accept and process the ARP request. So this is the first field, destination MAC address. Now we have another field, source MAC address. This is the MAC address of the sender device. Finally, the type. What's the type will be? The type will be that this one is an ARP message, and usually the type will be 0x, which means it's a hexadecimal number, 806. Simply. So we have 3 Ethernet packets directly frame, not packets, with the following headers: destination MAC, source MAC, type. Now, because the ARP is a broadcast, it will flood it out to all the ports on the switch except of the sending one. Now, all NICs must process the ARP message. They must process, mandatory. So all Ethernet on the LAN process the broadcast and must deliver the ARP request to its operating system for processing. So every device must process the ARP request to see if the target IP address matches its own routing table. Now, in case there is a match, they must what? Send a reply. So the request will send to the all device, but only one device will reply back to the request, not all of them. So what will happen after we sending the ARP request? We need to wait for the ARP reply. So same process. Only the device with the target IP address associated with the ARP request will respond with ARP reply. The ARP reply is encapsulated also as an Ethernet frame, and we will have the following headers: destination MAC, source MAC, type. Destination will be the MAC address of the sender. The device send the ARP request. The source MAC will be the source MAC address of the device. Send the reply. So to learn, we need this actually. We need this MAC address. The type will be the same, 0x806. So only the device that send the ARP request will receive the ARP reply, which means what? When we send the request, it's a broadcast. When we receive the reply, it's a unicast because we have specified the destination MAC and the source MAC. If you watch the video, you will understand it. It's very simple and easy. Now, what if the device do not receive any reply? We send the request but do not receive any reply. The packets will be dropped. Why? Because the frame cannot be created. We must add destination MAC address on the frame header. So we do not get the destination MAC address. So the packet will send. So let me re-explain it here. Now H1 want to send to H4. Now H4 have only the IP address. So H1 will send the ARP request. Please, any device with IP 192.168.1.7, give me your MAC address or send me your MAC address. What is this ARP request? It will be sent to the switch. The switch will send it back to all the connected ports. So it's a broadcast. Now any device should process the ARP request, which means accepted, send it to the MAC address, to the operating system. Now, if we have a find, now this PC will see, will it check the IP address, 192.168.1.7. It's my IP address, so I need to send a reply, ARP reply. So this device will send its MAC address to H1. So the source MAC address on the ARP reply will be what? The source MAC address is the MAC address of H1. The destination MAC address will be the MAC address of H4. Once H1 received the ARP reply, it will extract the MAC address. Now the MAC address is already known. I can send my packets directly, locally, to this destination MAC address. Now, remember, when we talk about the ARP table, we said it's stored on the RAM. It's temporary. It can be called ARP table or the ARP cache. So the entries on the ARP table are not permanent and are removed when the ARP cache timer expires after a specific period of time. So for example, what we have on the ARP cache, this one, IP address, its associated MAC. IP address, its associated MAC. The IP address. Now, if we do not use it, if we do not use the MAC within, let me say, 15 to 44 seconds or 45 seconds, this ARP entry will be removed from the ARP cache. So the duration of the ARP cache timer differs depending on the operating system. ARP table entries can also be removed manually by the administrator. So when we learn about or sending the request, receive the reply, then update our ARP cache, it will not be permanent. Once we do not use or send any message to this IP within this associated MAC for, let me say, for example, 45 seconds, it will be automatically removed from the ARP. What if I want to send later on a message? We must learn. How we will learn? We send a request, wait for the reply. After that, we can send our frame because we know what's the source and destination MAC address. واضحة؟ في أي سؤال قبل ما نكمل؟ تقريبا انتهينا، يعني مش باقي شيء. طيب, how we can see the ARP table? You have two options. We can show use show IBR command to display the ARP table on Cisco routers, or we can say ARP-A to display the address resolution protocol table on Windows 10 PCs. So this is how the output is looking like. Address, its MAC address, IP address, associated MAC, the IP address, and its associated MAC. Why we need the MAC? For the data link layer. IP address for the network layer. Now, we have a problem when we send the broadcasting ARP request or the ARP spoofing. So suppose PC1 send a message that a request, I need the MAC address of the default gateway. What's the default gateway? MAC address R1, this one, 00 minus 0D. Now, so the ARP request will be received and processed by all the devices on the local network. It should accept, pass the request to the operating system. Now, excessive ARP broadcasting can use some reduction in the performance. Imagine that many devices send the ARP request at the same time on the network. So the network performance will be reduced here. Now, ARP replies also can be spoofed by a theater actor to perform ARP poisoning attack. Simply, the gateway send its MAC address. We have here a hacker, let me say, but we'll not call it a hacker during this course. We call it threater actor. Threat actor. So the threat actor simply, instead of send the MAC address of the gateway, it send its MAC address to PC1. So what we call this poisoning ARP attack. So now whatever PC1 wants send it globally, it will not forward it to the router, it will forward it what? To the infected device. Threat actor device, to the malicious part. So, at the enterprise level, switches will include mitigation, a solution, techniques to protect from the ARP attack. What they will know or what they will use, usually they use something called DAI, Dynamic Address Resolution Protocol Inspection Mitigation Techniques to handle the ARP attack problem. So what's the attack? Simply, we are going to reply to this request instead of the gateway. So BCC will send its MAC address as a default gateway. So in this case, whatever want to send outside is sent what? To the threat actor side, not to the default gateway. Now, ARP is implemented for IPv4. What about IPv6? IPv6 will use a neighbor discovery messages to learn or to associate the logical address to a physical address. So IPv6 neighbor discovery protocol and D provide the following: address resolution, router discovery, and redirection services. Before we talk about these address resolution, router discovery, redirection services, we need to know what's the type of the messages sent by ICMP v6, Internet Control Message Protocol version 6. It's like the ARP. It's used to learn or to associate the IP address with its MAC address. But we have 5 types of messages to perform address resolution, router discovery, or redirection services. What are the messages? Neighbor discovery,
or sorry, neighbor solicitation message, neighbor advertisement message, router solicitation messages, router advertisement messages, and redirect message. So 5 types of messages for 3 services. One more time, what are the messages? Neighbor solicitation, neighbor advertisement, router solicitation, router advertisement, redirect message. Now, Internet Control Message Protocol v6 uses neighbor solicitation and neighbor advertisement. Messages will be used for device-to-device message, such as the address resolution. What's the MAC address for this IP address? So the request is neighbor solicitation. The reply will be router advertisement or neighbor, sorry, advertisement. Router solicitation and router advertisements messages are used for a message between devices and routers for router discovery. Finally, redirect message will be used by the router to know the better next hub or select the next hub. So IPv6 or ICMP v6 neighbor solicitation message are sent using a special Ethernet and IPv6 multicast addressing as well. It will not be a broadcast, it's a multicast. This allows Ethernet's NIC to receive the device to determine whether the neighbor solicitation message is for itself without having to send it to the operating system. So it's not a broadcasting neighbor solicitation message. It's a multicast, which means the device will check, is it for my multicast group? If yes, it will be processed by the operating system. If no, it will be discarded. So it will not be processed by all NICs like ARP message. It will not be passed to the operating system by all the NICs. So IPv6 device used neighbor discovery to resolve the MAC of the known IPv6 address. ICMP version 6 neighbor solicitation message are sent using a special Ethernet IP address, IPv6 address multicast. Only devices within that group will receive the neighbor solicitation message. What about the other? We'll discard it. So this is an example. BC1 send the neighbor solicitation message. Hello. I have, hello, who have or has the MAC address of this IPv6 address. So now it's the IP address of BC2. BC2 will send the neighbor advertisement message. Hi, this is my MAC address. So as you see here, the source address now is the IPv6 for BC1. And the destination is the IPv6 of BC2, and BC2 will send also its MAC address, which will be added to the MAC entry table. Now, ICMP in full details also with its attacks, mitigation will be discussed, inshallah, in T216A. This is the end of now